All right, we're gonna do Cramer's rule and other subtopics about Cramer's rule, including the inverse of a matrix. Um, so this is very algebraic. We are using a lot of algebra to do this. Um, let's start with an example. Let's say we have 2x plus 3y equals 4. Um, 5x plus, let's change that to 7y equals 8. Okay, so we have a system of equations and we want to solve this. Um, we're going to apply it. I'm going to show you how Cramer's rule is applied. So first we find the determinant of the system, which is just the coefficients without the constants. And there are many notations for this. I'm going to use delta for the determinant of the system, which in this case is going to be 2, 3, 5, 7. Now, there are other notations. This is the one I learned way back in the, I don't know, 80s or so. Um, but there's other notation. Some people will say the determinant of the matrix A, which is the main determinant of the coefficients of the system. So we find this, and it is 14 minus 15, or negative 1. Okay. And then we find the determinant on x. That can mean different things in calculus. So right now it means just the determinant. And I'm using delta because delta D determinant. Um, okay. Now, what we do is take this matrix, 2, 3, 5, 7, wipe off the column of the axis, which is the 2 and the 5, wipe that off, and replace it with those constants, 4 and 8. Okay, so we got 4, 8 in that column, 3, 7, and find that determinant. So that is 28 minus 24, 4. And then delta y is the determinant from the original matrix, the original coefficients, wipe off the column of the y's, the 3 and the 7, and replace it with 4 and 8, with the constants. But keep the 2 and 5. So we're not going from this to that. We're going back to the original delta and changing the second column with 4 and 8. 4, 8, and the first column remains 2 and 5. So again, I'm repeating, it's not that we are going from this matrix to this one. We're going from the original to this one. And that's going to be 16 minus, that's a 4, minus 20. 16 minus 20 is negative 4. I'm just puzzled because we got negative 4 again. That was a pure coincidence. I just made this up. Okay. So what does that say? Well, it turns out that x will be the determinant on x, delta x over delta, which in this case is, let me just double check this, 20, oh, this is positive 4. So we don't end up with exactly the same number. This is positive 4. 28 minus 24 is positive 4, as opposed to 16 minus 20 is negative 4. So we do positive 4, which is delta x, determinant on x, that's what I call it, over the determinant of the system. And so that is 4 divided by negative 1 is negative 4. And y is delta y over delta, and that is negative 4 over negative 1, and that is positive 4. So apparently x equals negative 4, while y equals positive 4. Well, let's check. Negative 8 plus 12 is 4, so that checks. This solution checks on the first equation, but we should check the second equation as well. Negative 20 plus 28, 8, yep, that checks. So indeed, that is the solution. All right. If I ask you to find or to solve a system of equations using Cramer's rule, please make sure you show all your work, all your determinants. Let's do a second problem, a longer problem, 3 by 3 problem. So let's say we got x, rather 3x minus 2y plus z equals, I don't want to use too big of a number, but 6. How about x minus y minus z equals 8, and 2x plus y plus z equals 9. Okay, so we got our system of equations, and we want to solve it using Cramer's rule. So it's very algebraic, very computational. We just go ahead and start working on the computations. Now, in a 3 by 3 system, rather in a 2 by 2 system, 2 equations and 2 unknowns, we need 3 determinants. The determinant of the main coefficients, and then 2 more determinants. Here we're going to need the determinant of the main coefficients plus 3 more determinants. So we're going to do a lot of determinants, 4 determinants total, and it's fairly labor intensive. There are some advantages of Cramer's rule, though. Even though it is very labor intensive, there's a lot of computations to be made, as for instance, opposed to elimination. In elimination, we quickly get to z. Here, even if we fairly quickly go find one value, we still have to go to a second value. I suppose we could do back substitution, but if we want to find all the solutions using Cramer's rule, we should really do all of those determinants. Yeah. Anyway, so the main determinant, delta, I call it, but again, different books call it different names. So just be aware of that. -1, -1. So 1, -1, -1, 2, 1, 1, 2, 1, 1, 3, -2, 1, 3, -2, 1. And we don't use those at all in our first determinant. Now, you could start simplifying by using row operations, because the row operations, as far as adding or subtracting a multiple of another row from one row, does not change the value of the determinant. And I'm thinking, well, we could subtract, 3 times that, 3 minus 3 times that. Sometimes, though, we spend too much time doing that, trying to optimize and adding and subtracting things. In fact, with a determinant, since the determinant of a transpose is the same as the determinant of the main matrix, we could do column operations just as well, and get to to a simplified with a lot of zeros determinant, and then go from there. Or even an upper triangular. If we try to make it upper or lower triangular, then we just multiply the elements on the diagonal. But what I have found myself is that in a 3 by 3, you spend too much time trying to optimize, almost more time than if I just figure it out straightforwardly and that's it, with the cofactors. So that's what I'm going to do, because again, sometimes it's not worth it. 3 times, especially if you have a good visualization of how to find the cofactors, 3 times, okay, so this is going to be -1 plus 1. Oh, that's 0, so that was actually not too bad. And then we do minus -2, because we multiply by the opposite of the next element. And then we got 1 plus 2, 3. And then plus 1 times 1 plus 2. Oh, 1 plus 2 again, 3. Okay, so that turns out to be 0 plus 6, and then plus 3, equals 9. Okay. Delta x. So we're going to do 3 more determinants to figure out the values of x, y, and z. So we wipe off this column and replace it with 6, 8, 9, 6, 8, 9. And the other 2 columns remain the same. -2, -1, 1, 1, -1, 1. All right, so same drill. 6 times -1 plus 1, 0. Minus -2 times 8, plus 9. 8 plus 9. Because of that negative, that's 17. Okay, and then 1 plus 1 times 8, plus 9. So that is 17 again. Oops. Okay, so we end up with 2 times 17, 2 times 17, plus 1 times 17. That is 3 times 17, and I happen to know that that is 51. Okay. Now, at this point of the game, we have an answer. We know x will be 51 over 9. We do know that, assuming that I didn't make any mistake, of course, on my computations. So we know x is 51 over 9. And we could try to simplify this, move this on the other side of the equation, and actually have a system of 2 equations and 2 unknowns, because one of them will be redundant. So we could do that. But then one thing that I have seen is that by doing that, we are going to end up with a bunch of fractions with denominator 9. I don't think this 9 has anything to do with this 9. Those are 2. That is a coincidence. But again, if we start working with 51 over 9 and trying to simplify this and keep solving it, which we could do, the problem is that then we have to work with a fraction that contains 9 as a denominator, and we got to do a lot of fraction computations. Here, there was no fraction at all whatsoever. So that's one of the reasons why I prefer this method, not all the time, but sometimes. So let's take the original columns, so 3, 1, 2, and then replace the second column with the constant 6, 8, 9, 6, 8, 9. Whoops, I goofed it up. Where's the eraser? There it is. Because I'm not close in the Anyway, so then we have a 1, -1, 1. 1, -1, 1. All right, so let's figure this determinant. We have 3 times, again, 8 plus 19 plus 9, 17, minus 6 times 1 plus 2, 3, plus 1 times 9 minus 16, that's -7. Again, 9 minus 16 is -7. So we have -18 minus 7 equals -25. All right, so now we know that the y is -25 divided by 9, another fraction, and that does not simplify. Oh, by the way, 51 over 9, I just realized right now, it does simplify. 51 over 9 is 17 over 3, because the 3 goes into 51. 17 times. So we end up, we have to simplify that if when we present our solution. Yeah. But again, so that simplifying complicates things, because if I wanted to find z at that point, we could, since we already know that x will be 17 over 3. Yeah, so actually the 3's cancel off, and that wouldn't be too bad. The y is negative 25 over 9. That does not simplify at all, but then we have a fraction. Well, we have to combine those two. We move them to the other side of the equation, which is going to end up being a fraction, and then we're going to subtract the fraction. So we could solve for z. That's an algebra problem, an algebra 1 kind of problem, but we're not going to do that. We could, and that should give us the correct answer. We're going to continue with determinants. So determinant in z is going to contain 3, 1, 2. We're going to go back to negative 2, negative 1, 1, negative 2, negative 1, 1, and then 6, 8, 9. 6, 8, 9. Okay. So let's see, that's 3 times negative 9 minus 8, negative 17, plus 2. So I'm going to skip a step, and instead of doing minus negative 2, because of the position of that entry, I'm going to put plus 2 right away. And then we have 9 minus 16, that's negative 7. And then we have a 6, and that is going to be 1 plus 2, 3. So that is negative 51 minus 14, and then plus 18. So those two add up to 4, and that means we have to do negative 47. Okay, I'm not going to give the final answer yet because I want to double check. So it looks like, well, this is sort of the final answer. X is 51 over 9. I know that that's simplified, but I'm not going to give it as a final answer yet because we're going to check, double check. Y will be negative 25 over 9, and Z negative 47 over 9. The reason why I don't want to simplify that yet is because I want to double check my solution, especially if you're doing this for an assessment, for a quiz or a test. You don't want to turn in your work without checking, because you could easily lose points that that you don't have to. Okay, so here we have 3x minus 2y plus 1z. So 3 of those, 3 times 51 over 9, plus 2 of those, 2 of the negative 25 over 9. Did I put plus? Oh, it should be minus, not plus. So we have a minus, okay, and then plus a z, plus negative 47 over 9. Now, I don't want to know what it is yet. I mean, I know it's 6, yes, but I'm going to pretend I don't know, because if I don't end up with 6, then I know one of the solutions, at least one of them, is wrong. All right, so 3 times 51 is 153. And then we got a double negative, so that actually makes it a plus 50. I'm getting a little worried, to be honest, because this is not looking good. I think minus 47. All of them have a denominator of 9. So that really means we are adding 3, because 50 minus 47 is 3. So we have 150 6, 156 over 9, and that does not divide by 9 evenly. So I'm gonna pause this video for a moment. Yep, and I just found where the mistake is here on this. Well, first of all, please know that this was supposed to give us 6 because we're checking the first equation. So I know I made a mistake. That is it has a value to know how to check at least one way to check when we make a mistake. There it is. 3 times 17 is 51. For some reason, I neglected to write that down. 51 positive minus 18 minus 7. So that is actually negative 25 plus the 51. So that is going to give us 26. So that is incorrect. That should be 26 positive. 50, again, those are 25. If it was 50 minus 25, the answer would be 25, but this is one more, so the answer should be positive 26, which means this should be positive 26. So this is positive 26. All right, and that means we have to subtract 52. All right, so 153 minus 52 is 101. 101 minus 47 is 54. So that should be 54. And we do know 54 divided by 9 is 6. Okay. Boy, that was a little stressful for a moment, at least for me. So now let's move on to the second equation. The second equation is the first minus the second minus the third. Okay, so 51 over 9 minus 26 over 9 minus negative 47 over 9. Now let's see, I on purpose moved the page, the original problem quickly because I didn't want to know what it was. 51 minus 26 is 25, but then we're going to add 47. That's 72. 72 over 9, and that I know is 8. And I do remember on the last column, we had 6 and 8. Okay, now I'm going to look at the last row, 2x's plus a y plus a z. And I noticed how I'm blocking this. I don't want to know what it is. I kind of remember what it is, but 2 of the first, 1 of the second, 1 of the last. So 2 of those, well, that's 102 over 9. 102 over 9. One of those, 26 over 9, plus 26 over 9, plus one of those, negative 47 over 9. So that is 128 minus 47. Well, that's got to be a 1 because of the 8 minus 7. 128. Okay, so the 12, I'm doing the subtraction in my head, minus 4 is 8. Yep, over 9. All of them have the same denominator. So we get 6, 8, 9. Okay, so now we're ready to write the answer. So the solution, now that we write the solution, we say, okay, that is 17 over 3. X should be 17 over 3. Y is the fixed number, 26 over 9. 26 over 9. And Z should be negative 47. Negative 47 over 9. So there's our solution to the system of equations using Cramer's rule. Now we can do a 4 by 4 system, a 5 by 5 system. We can do any number of systems. When the system is large, for example, 50 or more, this process is actually slow. Because there's a lot of computations that are going on. When I was doing the determinants here, I was skipping, the steps. I was kind of doing the 2x2 matrices or determinants just in our head. But there were actually many, many computations, and this is a fairly small system. So for a big system, this process is reasonably long. It's longer than elimination. If you write a program in which we do elimination, another program in which we use determinants, the Cramer's rule, then when we have a big system, again, 50 by 50, 100 by 100, or larger, then the Cramer's rule is going to take longer to compute. You're going to be waiting, while the elimination, boom, in a matter of a minute, you're going to get the answers. Determinants are going to take many minutes. If you have a system and time to do a system of equations that is large, even with simple coefficients, then we will realize that Cramer's rule is longer. But that doesn't mean that it is bad. One thing I do like about Cramer's rule is that we avoid fractions altogether. We did not compute anything with fractions other than checking. Yeah, the checking, sure. And even in the checking, we use the same denominator. So I wasn't really mixing fractions with different denominators when I was checking the answer. So through the whole problem, there was no fractions to speak about. No fractions here. It's all whole numbers. When we write the answer, we have a fraction, but there's no intermediate steps where we're using fractions. So one thing that I like about Cramer's rule is that we can avoid fractions, and that can also help us come up with solutions more neatly, because then the fractions show up right at the end, and then all we have to do is simplify. So that is an advantage. The other advantage of Cramer's rule is that it provides us with a solution immediately without having to, what I meant by that is, if we have variables in the constants, then it gives us the answer without hesitation. Let me give an example of that. Example 3. I'm trying to think what size of a system. Okay, so let's say you have ax plus by equals c, and then bx plus ay equals d. Okay, so we got this system of equations with unknown constants. But what we do know is that those two are flipped. Can we use elimination? For sure. We can multiply by b this equation, by a that equation, and then we can subtract, and we're going to end up with a b squared. And we can definitely use elimination. Cramer's rule gives us the answer very, very straightforwardly, without doing elimination, without thinking which one I'm going to eliminate. It's almost mindless in the sense that you just apply the formula. What is the determinant of the system? Well, it's a b a, and so it's a squared minus b squared. So as long as those two numbers are not the same, we're good, because we're not going to divide by 0. And then determinant on x will be cd, whoops, c, d, and then BA. So we have AC. If you say CA, that's the same thing. We usually we should put the letters in alphabetical order, but in ABC order. But I don't think I'll take points off for that. AC minus BD, yep, minus BD. There we go. The other guy is going to be the other determinant, AB, same column. Replace that column with CD. So then we got AD minus BC. And voila, there's the answer. X has to be AC minus BD, AC minus BD over A squared minus B squared, and Y has to be AD minus BC over A squared minus C squared. Yep. So it's very straightforward. We don't have to think what to eliminate with what. In a way, that is not a good thing, because when we start when we stop thinking, then, well, that's the problem. We stop thinking, and then we just plow numbers into a formula, and that's it. We're not thinking anymore. So there is some value, and then there are some drawbacks. It depends. As long as, I guess, as long as we don't abuse it. This is in contrast with elimination. I just want to emphasize that Cramer's rule is in contrast. Cramer's rule with elimination. So those two are, again, against each other. This gives us a formula. It works beautifully. Elimination also works beautifully. But then here we have to think. You have to do a conscious decision which one you're going to eliminate. How? Cramer's rule does not give us any of that. Okay. So the next application about Cramer's rule, I don't want to dwell on why Cramer's rules work. It just does. There's, if you read some books, they're gonna tell you why, and the reasons are good, but sometimes reasons are not are over emphasized or overvalued. Sometimes they're not. It depends on each situation, and even that is actually my opinion too. So it's not a fact that they are. Sometimes they are, and sometimes they aren't. In the case of Cramer's rule, why does it work? In my very, 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 very personal opinion, just because it does. Yeah. Well, it's a good. Sometimes that is a good answer. Sometimes it isn't. Many times it isn't. But one application is finding the inverse by using Cramer's rule or determinants. I'm kind of using Cramer's rule and determinants indistinguishably in this video. So finding what should we call it? Oh yeah, the inverse of a matrix. So let's say we have, as an example, for a matrix 2, 3, 4, 5. So that has an inverse, and we want to find its inverse. So that means we want to find a matrix. Let's call it X, Y, Z, W, that gives us the identity 1, 0, 0, 1. Okay. Now these are 4 unknowns, X, Y, Z, and W, and yeah, there's going to be 4 equations because we're going to multiply 2x plus 3z equals 1, and then 4x plus 5z equals 0, and then the same kind of thing with y and w. Okay, we can break this system of equations up into 2, 3, 4, 5 times xz equals 1, 0, and 2, 3, 4, 5 times YW equals the second column, because when we multiply with the first column of this matrix, we're going to end up with the first column of the answer of the product. Multiplying with the second column gives us the second column of the product. So 0, 1. Okay. And now let's do this system by Cramer's rule. Now I was going to skip why we can use Cramer's rule, but I'm going to just write it down to make it clear. So this really means 2x plus 3z equals 1, and 4x plus 5z equals 0. So this is the system we're going to solve by using Cramer's rule. And remember, we have to find the determinant of 2, 3, 4, 5, which we do now. So the determinant is the determinant of 2, 3, 4, 5, which is going to give us 10 minus 12 negative 2. Okay, comma. Determinant on x. Okay, so we're going to wipe off this column, and we're going to replace it with 1, 0, or this column and 1, 0. So 1, 0, 3, 5. So of course that's going to be 5. That's easy. And then I was going to squeeze that in there, but let's do it here. So delta z, yep, is 2, 4. Well, 2, 4. Wipe off the second column and replace it with 1, 0. And that's going to give us 2. So we can start writing the answer. So x is 5 over negative 2, or negative 5 over 2. Okay, so let's assume this is a. So I'm going to try to squeeze it in here. So a inverse will be 5 over negative 2, because that is 5, or negative 5 over 2. That is the x value. Z value is 2 over negative 2. Negative 1. And I'm going to check that. We're going to check that we actually get the right answer, but let's kind of finish this up. Now, here we have 2y plus 3w, 2y plus 3w equals 0, and 4y plus 5w equals 1. The thing is that the determinant we're going to use is the same determinant as the determinant for that system of equations. So we got really two systems of equations with the same determinant. So we don't have to do the determinant 2 times, because we already got it. It is negative 2. Okay. Determinant on y. Okay. So we're going to wipe off where's the y? There is the y. We're going to wipe off the 2 and the 4. And we're going to replace it with 0, 1. Watch out, though. We're not going to replace it with 1, 0. We're going to replace it with 0, 1. 0, 1, and then 3, 5. So that is negative 3. So this guy should be negative 3 over 2 because of that. And then determinant w, 0, 1, and then 2, 4 as a column. Whoops, 2, 4. My brain sometimes gets ahead of my hand. I don't know if that's an age thing or it's just me, but when I'm typing, recently I've been hitting one key ahead of the other when I'm typing. So when I type the, T-H-E, oftentimes I do T-E-H, and I think sometimes my head is getting, I don't know why. Anyway, so what is it? 2, 4. 2, 4 equals 2. Oh, 2 divided by negative 2 is going to give us negative 1 again. I'm puzzled by that. It doesn't seem that that should do. Well, let's check. That's the beauty of this. We can check. So 2, 3, 4, 5. we should be able to multiply with too many negatives. Why is that negative? Let me double check a couple things. So that's 5, 2 positive, negative 3 over negative 2. Oh, that should be positive. 2 positive. I think there's a mistake here. But let me, before we find the mistake, let's actually see how we are supposed to check. So negative 5 over 2, 3 over 2, negative 1, and then negative 1 again. Before we actually find a mistake, let's see why we know there's a mistake. So negative 5 over 2, yeah, minus 3, that is going to be negative, which is negative 6 over 2. So that is negative 11 over 2. Okay, so negative 11 over 2. Right there, we have to sound the alarm. There's a mistake because we're supposed to end up with the identity. Let me check. Yep, I see where the mistake is, right back here. 0 minus 4 in the DZ is the mistake. So 0 minus 4, boy, that is negative 4. So Z is this corner number. So we got negative 4 over negative 2 is positive 2. Okay, so we knew this was wrong. Apparently, if we just replace that with a 2, that will fix the issue. All right. So 2, 3, 4, 5, multiplying with a negative 5 over 2, 3 over 2. What did we say? Z was positive 2, and negative 1 will do. Okay, so negative 5 plus 6, 1. Okay, that doesn't mean we're good. We still have to check the rest. Negative, well, no, 3 minus 3, 0. Negative 10 plus 10, 0. So that's 6 minus 5, 1. Yep. So it works. All right. Example 5. Same thing, but now with A, B, C, D. So assume this is the matrix, and we want to find the inverse. Now, one method would be elimination. And we have done that before. But the other method is by determinants. So we want to find the determinant of the system. Delta will be just a determinant, which is AD minus BC. And then there are 4 more determinants to do because we got actually 2 systems of equations. So pretend instead of having 2, 3, 4, 5, we have A, B, C, D, which really 2 systems, 1 for this column, 1 for that column. And that means we have to do, let's see, boy. The first one is 5. The second one, if we look at this carefully, when we find this determinant, all we're doing is multiplying the 1 times the 5. So there's the 5. And here on the next column, the next entry of that column, what we are doing is the opposite of the 4. So the 5 as is, the opposite of the 4 here. Yep. So the 5 is going to end up there. The opposite of the 4 is going to be on this. Well, let's just do it. Okay. So remember, we want to find the determinant. So delta, assuming that this multiplied with, okay, so comma, x, y, z, w, and that is the inverse. Okay. When we multiply together, we're going to end up with ax. Let's write this down. So ax plus b z equals, and remember, we're multiplying to the identity, so we're going to end up with 1, 0, the first column, and then cx plus dz equals 0. Then we are going to have the second column, ay plus bw equals 0, because now we want the second column of the identity. The identity has column 1, 0, and then 0, 1. And then cy plus dw equals 1. Okay, boy. So we're going to end up with delta x equaling 1, 0, that column that is replaced, and then bd. So we end up with d. Okay. Delta z, z, so put 1, 0 in that column, the column of the z's, and then a c, and that's going to give us negative c. Delta y. Okay, so the y, we replace that with O1, that column O1, and then we still have BD. So the determinant is going to be 0 minus B. And delta W, rather, will be, whoops, I just messed that up too badly. Delta W is, okay, AC O1, so that is A. So the inverse will be D over that. AD minus BC. That's just the upper right, upper left corner. Z will be negative C over AD minus BC. The upper right corner of the inverse will be opposite of B over AD minus BC. And then the lower right corner of the determinant, where is it? This guy will be, there you go, A over AD minus BC. Well, all of them are divided by AD minus BC, so we can factor that out, and that is going to give us 1 over AD minus BC times D, opposite of B, opposite of C, A. There we go. So if we start with A equaling A, B, C, D, what this formula tells us, swap those two. You know, the A goes down here, the D goes there. Leave the B and the C's where they are, but change the signs. But make sure to divide by the determinant of the original matrix. Yeah, so the bottom line is that we can end up with a nice formula for the inverse. Now, don't assume we will just have single letters. If we have a 3 by 3 determinant, then yeah, we gotta get the main determinant out. But on top of that, we're gonna have the subdeterminants, which are gonna be the cofactors. Those are the cofactors in here. These are actually cofactors of a 2 by 2 matrix. Let's review what a cofactor is. Cofactor. Okay, and let's give an example just to make sure. This was example 5, so example 6. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 10. So pretend you got that matrix A, and let's find the cofactors, at least a few of them. The cofactor of this, and we're going to make a matrix of cofactors, which we're going to label as C for cofactors, a 3 by 3 matrix with the corresponding cofactors. So the cofactor of 1 is going to be, if you wipe off this column, the column of the 1 and the column of the 1, and the row of the 1 rather, we're going to end up with a smaller matrix, a 2 by 2 matrix. The determinant of this matrix will be the cofactor. So that is 5 times 10 is 50 minus 8 times 6. So 50 minus 48 is 2. That's the cofactor corresponding to 1. And it is found by doing 50 minus 48. The cofactor of 2 is going to be 40. So wipe off the column of the 2 and the row of the 2. And we end up with 4, 6, 7, 10. Find the determinant of that 2 by 2 matrix. The matrix 4, 6, 4, 10, which is going to be 40 minus 42. That should give us negative 2. But because we're on the second entry, we're going to turn that into opposite. So 2 again. Okay, let me remind you the matrix of signs, which starts out with plus, minus, etc., and then minus, plus, etc., and then plus, minus, etc., and so forth. So when we find a determinant by wiping off, by erasing columns and rows, we're also going to multiply, in addition to that, we're going to multiply by one of those signs, depending on the position we are, depending on the cofactor. So the cofactor of this 2 is going to be 40 minus 42. It's negative 2, but we're going to multiply by negative because this position corresponds to the negative. Thus, we end up with 2. The cofactor of 3 will be 32 minus 35, negative 3. And we keep it as 3, rather, and we keep it as negative 3 because we don't do opposites. All right. The cofactor of 4 is 20 minus 24, negative 4. But that position is negative, so we have to do a negative 4. Let me double check. 20 minus 24 is negative 4, positive 4. Cofactor of 5, 10. So I'm doing 1 times 10, 10, minus 21, negative 11. Keep it as is. The cofactor of 6, 8 minus 14, negative 6. But we are on this position, so we have to do positive 6. The cofactor of 7, 12 minus 15, negative 3, leave it alone. Because that, so plus means leave it alone. Minus means do the opposite. So this, whatever answer we get for this cofactor, the cofactor of this 8, we got to do its opposite. 6 minus 12, negative 6. opposite 6. Cofactor of 10, 5 minus 8. 5 minus 8, negative 3. Okay. We are about one step, well, 2 steps short of finding the inverse. So right now, I was just explaining the cofactors, how to find the cofactors. Make sure you know how to do the cofactors. Once you know the cofactors, which are actually subdeterminants of the main matrix, there's 2 steps we got to do. We got to find the transpose of this matrix, and we're almost to the inverse. So the transpose of C transpose is, okay, 2 to negative 3 will be a column. 2 to negative 3. 4, negative 11, 6, another column. Negative 3, 6, negative 3. I'm going to multiply with the original matrix A. 1, 2, 3, 4, 5, 6, 7, 8, 10. So again, we took the cofactor matrix 2 to negative 3, made it a column for of the first row. Second row, 4, negative 11, 6, negative 3, 6, negative 3. So that is the transpose, original matrix A. Let's multiply and see what we get. So we get 2 and 4 minus 9. 2 and 4, 2 and 4 is 6 minus 9, negative 3. 4 minus 22 plus 18. Okay, so 4 plus 18 is 22, minus 22 is 0. Negative 3 plus 12 is 9, minus 9 is 0. 18, 18 minus 18, 0. Negative 12 plus 12. No. Negative 12 plus 30. Negative 12 plus 30. That's not good. I'm already doing the last row. That's okay. Let's finish that one. Negative 12 plus 30 is negative 8. Negative 12 plus 30 is positive 18. Minus 18 is 0. 16 minus 55 plus 36. Boy. Let's do 36 plus 16. 36 plus 16. Let me do it real quick here. 36 plus 16. 52. 52 minus 55 is negative 3. Okay. Boy. 14 and 16. That's 30 minus 30 is 0. 28 minus 88 plus 60. Well, 28 minus 88 is negative 60 plus 60 is 0. And then, boy, negative 21 plus 48 minus 30. Boy, that's not easy. 6 times 8 is 48. Okay, so I'm going to start with 48. Minus 30 is 18. Minus 21 is negative 3. So we don't end up with the identity. but we are really, really, really close with obtaining the identity, as you can tell. It's almost the identity. So this means that this is not the inverse of this, but we are close. If we divide by 1/3, well, if we divide by -3, or if we multiply by -1/3 to keep the equal relevant, we have to multiply with that. And then we have the identity, the 3/3 identity. Okay. We usually just put 1/3, not 3/3, but same thing. All right. So where does that come from? Well, it turns out that -3, which is what is causing this to be not the identity, is the determinant of the original matrix. If we find the determinant of the original matrix, it will be -3, unless I'm wrong. Let's just double check. 1, 2, 3, 4, 5, 6, 7, 8, 10. So using cofactors again, that is 50 minus 48. 50 minus 48 is 2. And then minus 2 because of the position of that 2. That's why we use minus. 40 minus 42 plus 3. 32 minus 35. So that is 2 plus 4 minus 9. Sure enough, the determinant of this matrix is -3, which is the extra factor we have. So we have a formula for the inverse. The inverse is 1 over the determinant of A times the transpose of the cofactor matrix of A. And there we have it. We have a formula for the inverse. Yep. Using the determinants and Cramer's rule. There is another application. So one application of Cramer's rule is to be able to find the inverse of a matrix. There's another application of Cramer's rule, and that is about the volume of a parallel pipe. I forgot to check the spelling, the correct spelling of parallel pipe. I think that's correct, but please double check. What is a parallel pipe? It is a solid whose base is a parallelogram. Parallelogram, and the side is also a parallelogram. Boy. That kind of looks like a box, but it's not meant to be a box. So let me draw another picture. It's not a rectangular box. So let's make the angle kind of sharp here. So this is a parallelogram. The base is a parallelogram, and also the sides are parallelograms. Although here they look very rectangular, but suppose those sides are also, everything is a parallelogram, and the opposite sides are of the same congruent. They are congruent. So opposite sides are congruent, opposite sides are congruent, top and bottom are congruent, those two sides at the end are congruent, and those sides are also congruent. Now, this is formed by 3 vectors. If this is the origin, and this is vector A. So this is the vector A. Yeah, I'm not going to put an arrow on top of it, but that's a vector, a three-dimensional vector. And this is vector B, and this is vector C. Yeah, so A would be A1, A2, A3, and B is B1. Well, column vector, but it doesn't matter. B2, B3, C equals C1, C2, C3. Then it turns out that the um, the volume of this parallel pipe is equal to the absolute value so ABS for absolute value of the determinant of the matrix A1, A2, A3, B1, B2, B3, C1, C2, C3. And you can put them as columns or rows. It doesn't matter because the determinant of the transpose of a matrix, square matrix, is the same as the determinant of the regular matrix without transposing it. So it doesn't matter whether we use columns or rows. The determinant is going to be the same. That determinant could be positive or negative, or it could be zero. When we take the absolute value of that determinant, then we're going to end up with a positive number or zero. If the three numbers are, rather, if the determinant is zero, that means that the three vectors, actually the four vectors, are coplanar. The origin A, B, and C are coplanar if and only if this volume is equal to zero. Three vectors are always coplanar, so we have to include O. O is one of the corners. The origin is one of the corners of this parallel pipe. Yes. There is one more introduction. I'm going to actually two more things. The cross product of two vectors. Now, cross product only exclusively applies to three-dimensional spaces. Cannot be used in 2 dimensions, 1 dimension, or 4 dimensions, or anything else other than 3. So this is exclusive to three-dimensional space, cross product. If you have two vectors, V and W, and they don't have to be 90-degree. If you have two vectors and you find the cross product, which we're going to denote with V cross W, we're going to end up with a vector, so VW, with a vector that goes this way. Yep. And it will be perpendicular to, so this is V cross W to V, and it will also be perpendicular to W. So we're going to end up with a third vector, V cross W, that is perpendicular to those two. We use what is called the right-hand product, which means if we multiply V with W, pretend you're going to screw a bolt, and because we're doing righty-tighty, the bolt will be going in this direction. If you do W times V, then you're going to end up with a bolt going that way. So righty-tighty, lefty, loosey. Is that how it goes? Loose. Anyway, so it goes the other way if we do W. So this is not, I don't have enough room to put it. Should typically, not necessarily, but if those two vectors magnitudes are greater than 1, then the magnitude of this guy is going to be bigger than 1. If those two vectors have a magnitude that is smaller than 1, then this vector is going to be shorter than 1. Yeah. But pretend that's, so this is a little longer than that. So this would be W crossed V. Yep. Or the other way to put it is, if you Yeah, if you go, pretend you're underneath and then you turn it from W to V, but then you can say, well, how do you know you're turning it? Because you can go in this direction and go from W to V, or you can go in this direction, go from W to V. So it is the shorter of the two is what counts. So we go from W to V, yeah, and that gives us this vector, which is the cross product. This is used extensively in physics, all the time in physics. So let's show how we do that. Um, so let's say you have V1, V2, V3, that's V, and we want to cross it with W, W1, W2, W3. Here's the formula I use. So first, I pretend I put them one above the other, V1, V2, V3, because I'm using sort of cofactors, W, W3. You know, pretend you got another row up here. And so this is like a matrix that is 3 by 3. If you pretend there was a row up here, so I do V2, W3. So V2, W3 minus V3, W2, comma. So that is just the first component of this product. So there's three components. And then we do negative V1, W3 plus W1, V3. I'm running out of space and I don't want to write it too small in here. So I'm going to continue with a third coordinate down here, V1, W2 minus V2, W1, or W1, V2, either way, close. That's the way you pretty much have to memorize the way to find the cross product. At least I do memorize it. And why does it work? I hate to give this answer because it's not a very insightful answer. It works. It just does. An analogy that I like to give to students is, why do we have two arms and two lungs and two kidneys and two of a lot of the stuff? We two eyes, two ears, and I think it works really good. It's simply because it works well. If we have three arms, how do you keep them balanced? Two arms are usually balanced. There are two legs. Is three legs better? I don't know. It doesn't seem to be better because just it just works really well. And then if we lose one arm, then we still have the other arm. But three seems excessive. One is too few. So two seems to be working really well. So why does it work? It just works well. I know this is not a very insightful answer, but sometimes those kind of answers are the best answers. And that's my opinion only. So another analogy that I like to give is, why do vehicles, like cars, have four wheels instead of, on the ground instead of three or two, like a motorcycle? Well, four works really well. Five is excessive. Three is unstable. Otherwise, many vehicles would have three. Um, so four seems to work really well for trucks and regular buses and regular um, cars. Four is a good number for vehicles. Uh, Two is a good number for organs, and so forth. So why? Because I think because it works really well. Well, this works really well. As far as telling us a lot of information about the two vectors we're utilizing to come up with the cross product. Um, yeah, so this is used to measure torque, for instance, because if you are turning uh, a wrench, if you double the length of the wrench, you're doubling the force that you're applying on the bolt, for instance. And yeah, so we want a formula that so that if we double um, if we double the distance, as it can happen in a wrench, then the torque, which is the cross product, is also doubled. Now, when we are talking about a wrench, what are we doubling? Or what are we crossing? We're crossing the way in which we push the wrench. but that gets more into physics. Let's practice a little bit of the cross product. Yeah. So there are many applications of the cross product. So let's 7. Example 7. Okay, let's find the cross product of 1, 2, 3, and 4, 5, 6. Let's see what it is. So the way I visualize it, I don't, I guess we don't have to put one above the other, but I do. That's my way. And if you look at different books and different places, then you're going to get different ways of doing this. But this is my way. So I go 18, no, rather 12 minus 15, negative 3, comma. And then we got 6 minus 12, negative 6. But because of the position, we have to have the opposite. Now I forgot what it was. 6 minus 12 is negative 6, so 6. And then 5 minus 8, negative 3. So the cross product is this. The cross product of this vector with this vector. Okay, so that's the answer. That's the cross product. What does that tell us? If we do the dot product of those two, we end up with negative 3. Okay, so 1, 2, 3 dotted with negative 3, 6, negative 3 will be negative 3 plus 12 minus 9, which is 0, which means those two vectors are perpendicular. How about those two? 4, 5, 6 dotted with negative 3, 6, negative 3, negative 12 plus 30 minus 18. And that's going to be 0 again. So that means that this new vector is double those, no. It is perpendicular to those two vectors. In addition to that, we get more information. Between two vectors, there is an angle in between the two. And it's by angle, we mean whenever you have two lines that are crossing each other, there's two angles involved. You know, there's this one and then there's this one. Whenever we have two vectors and we're talking about the angle in between them, we always mean the shorter of the two. So something about the cross product is that the cosine of theta is equal to the cross, well, let me write it differently. The cross product of VW, V cross W, is equal to the magnitude of V, magnitude of W, times the cosine of theta. There we go. So the cosine of theta is equal to the cross product divided by the magnitude. So we get a lot of information. In particular, the cosine is 0 when there is 90 degrees. The other way around, sorry. The cosine is 1 when there is 90 degrees. So it is this product is maximum. This product is maximum at 90-degree angles. It is minimum at 0 or 180 degrees. So this product, again, is maximum at a 90 degrees, which measures torque really well, in particular, torque. You know, if you're pushing, if you're turning something, it's better to keep 90 degrees between the force and the object, the bar that we are. So if I push this way, I'm not really turning anything. So that is 0. I want to be able to measure. And if I push this way, I am turning, but less effectively than if I push at a 90-degree angle. So the best way to turn is to keep 90-degree angle with respect to the bar that we are turning. And The cross product measures that really, really, really well. It measures the maximum very well because it is attached to the cosine. That is geometric. That works really, really well. And so that's why we use it. There are some properties of cross product, and there's also the triple product. Yeah, triple product. I'm going to let you read that, but the triple product of u, the vector u, v, and w is u crossed v, and then dotted with w. So that is the triple product. And I'm going to let you read that. And we're going to close this video here. Okay.